Okay, so we've set up the same functions, and we've got our displacement field. There's just one sanity check I want us to do before we proceed. And the sanity check, what we do is, I want to say to you, if I were to choose that each node, okay, displaces the same amount, I want to give this structure a rigid body motion. I just want to make sure that essentially we do recover just a rigid body motion, but we don't have sort of all of a sudden stresses and stuff in the structure or strains in the structure. So if I were to say, imagine, let's give this node the same displacement as this node and this node, so that each node displaces the same amount along x. Okay, and let's draw this. What I mean is make sure that we're on the same page. If I say this node displaces this much, this node displaces this much, displaces this much, so that in the end the deformed structure is just there, and that this distance here is, let's say, let's call it delta x, and delta x my displacement. If I call it like that, I want to make sure that indeed it recovers that. So what would be required for that to hold? What would be the requirements? So let's see. So this is my displacement field, remember, at any psi. So I've got the unknowns at q1, q2, and q3, but I can evaluate for any psi. So what I want to do is to say, let's say u is a function of psi. Okay. If I say n1, I'm give it the same displacement. Now I'm going to do this experiment plus n2 delta x plus n3 delta x. Okay, that's it. So I've given each of these unknowns the same, because I can do that because they've got meaning. Remember, q1, q2, q3 are just the displacement of that node. So I know for a fact what I would want to happen is for any psi, doesn't matter what psi I evaluate. If I evaluate the structure and ask you how much it needed to displace, so that there is no stress and stuff for me, it needs to displace the same amount as this node or this node or this node. They all need to be delta x. Any place where I evaluate the field, it needs to say the displacement is just delta x. Okay, so we can write that and say, make sure I'm not off. I can just pull out the n1 plus n2 plus n3 multiplied by delta x. Okay, and I want this to evaluate for any choice of psi to just delta x. Then I know this thing will have nice rigid body motion that won't have any stresses or strains. This is just a sanity check, because we didn't enforce anything here. We just constructed these cost functions. We didn't enforce any of those conditions, but we want to make sure that just basics are not just broken up front. Okay, so the reality is we need to make sure that this, if I sum these same functions together, that they sum to equal to 1. Okay, so that's important to understand. If I have n1 as a function of psi plus n2 as a function of psi plus n3 as a function of psi, I would like to make sure it always adds up to 1. Okay, and the reason for that is just I want it to be able to at least tell me that there's no stresses and strains when I just move something rigidly in space. Otherwise, things are quite broken. Okay, so let's see what happens if I add these together. If I were to say minus a half psi 1 minus psi, what was that? Plus a half psi 1 plus psi plus 1 minus psi 1 plus psi. Okay. Where are we going to continue? This I'm going to wipe off. We've now discussed this. We understand this. Not a problem. So let's just expand this and say, and this is something we can pause the video. Please go and do this in SymPy. It's a good example just to double check with SymPy in case we make a mistake. Okay, so let's just multiply all this out. It's minus a half psi, okay, plus a half psi squared. So these are the two terms, this and this. Okay, this is plus a half psi plus a half psi squared. Okay, and then this, if I multiply this out, is plus 1. Yeah, this 1 and 1, and then it's minus psi plus psi. So they will cancel out. Let's just write them out there. Minus psi plus psi, and then this will just be minus psi squared. Okay, let's see what cancels out with what. So minus a half psi and plus a half psi will cancel out. Okay, this becomes just psi squared. Oh, it will cancel with this one. Minus and plus psi, and I'm left with 1. Indeed, if I say N1 plus N2 plus N3, it does evaluate to 1. Okay, so this is an important thing. In the way I've showed you how to construct shape functions, to a large extent will have this kind of property. But it's always something you need to double check. So this is why we can't just make up stuff for shape functions. Like, for instance, say I want to use sines and cosines. Okay, because often when you have these kind of formulations, it doesn't have the property when you add the shape function together that it equals to 1. And this is not just a wish listing, it's a basic check based on physical reasoning, okay, that we had here. This is not, I'm not asking for this because of esoteric conditions. I'm asking you that we need to satisfy this. Otherwise, we can't even represent this, which is just rigid body motion of a structure. We say all of a sudden there's lots of stresses involved. That is going to be a rubbish kind of approach from the get-go. Okay, so this hopefully gives you a good idea of what shape functions are, how a displacement field looks, and just one of the many properties that we'll still look at that the shape functions should have, just as a sanity check that this is at least sensible what we are doing. That from the beginning, when we get going, we at least can say we check the sanity check. Say this is at least something that seems like it would work.